The philosophy of physics tackles big questions: the nature of space, time, matter, and the laws governing them. It's about understanding the very fabric of our universe. Let's break it down with the three pillars of modern physics: quantum mechanics, relativity, and statistical mechanics. First up, quantum mechanics. You ever wonder what a quantum state really is, or why measuring something changes it? This pillar explores the weird world of entanglement and the quantum classical relationship. Next, relativity. This pillar digs into the nature of space-time causality and how it all fits with quantum mechanics. Lastly, statistical mechanics. This is where the microscopic meets the macroscopic. We're talking about the origins of irreversibility, the arrow of time, and how probability and entropy play a role in the universe. But that's not all. Philosophers of physics also ponder the nature of physical laws, symmetries, and the role of mathematics. New fields like quantum gravity and complex systems bring even more questions to the table. The existence and nature of space and time, or should I say space-time, are central topics in the philosophy of physics. So what are the big questions here? One major issue is whether space and time are fundamental or emergent properties. In classical mechanics, time is taken to be a fundamental quantity, something that can't be defined in terms of other quantities. But theories like loop quantum gravity suggest otherwise. As Carlo Rovelli, one of the founders of loop quantum gravity, puts it, no more fields on space-time, just fields on fields. So what does this mean for time? Time is defined via measurement. Both Isaac Newton and Galileo Galilei, as well as most people up until the 20th century, thought that time was the same for everyone everywhere. But then came Albert Einstein and his theory of relativity. According to Einstein, rates of time run differently in different inertial frames of reference, merging space and time into a single entity, space-time. This theory, along with the redshift of light from receding galaxies, suggests that the universe, and possibly space-time itself, began about 13.8 billion years ago in the Big Bang. Einstein's theory of special relativity made the idea of a privileged present moment much less plausible, as time appears to be reference frame dependent. And what about space? Space is one of the few fundamental quantities in physics. It's defined via measurement, just like time. Currently, the standard space interval, or simply meter, is defined as the distance traveled by light in a vacuum during a time interval of 1,299,792,458th of a second. In classical physics, space is a three-dimensional Euclidean space where any position can be described using three coordinates and parameterized by time. But special and general relativity use four-dimensional space-time. There are even speculative theories that propose more than four spatial dimensions. Quantum mechanics is a major focus of contemporary philosophy of physics, especially when it comes to its correct interpretation. One of the most perplexing aspects is the concept of superposition. Imagine particles not just being in one place at one time, but existing here and there simultaneously. This radical view challenges many of our common sense metaphysical ideas. Much of contemporary philosophical work in quantum mechanics aims to make sense of what the highly successful formalism of quantum mechanics tells us about our physical world. Take, for instance, the uncertainty principle. This principle asserts an upper limit to the accuracy with which pairs of conjugate variables, like position and momentum, can be measured simultaneously. It arose from the question, how does one measure the location of an electron around a nucleus if an electron behaves like a wave? The principle reveals a fundamental limit to our knowledge, illustrating a core concept of quantum mechanics, that uncertainty is inherent in the nature of quantum systems. Then there's Bell's theorem, which presents a fascinating paradox. It suggests that quantum mechanics is incompatible with local hidden variable theories, challenging the principle of locality, the idea that a particle can only be influenced by its immediate surroundings. Bell's theorem tells us that either measurements on one particle can influence another particle faster than the speed of light, or that quantum particles carry unknown properties or hidden variables. Subsequent experiments have consistently supported the predictions of quantum mechanics, suggesting non-locality is a fundamental aspect of our universe. The Copenhagen interpretation, formulated by Werner Heisenberg and Niels Bohr, posits that quantum mechanics is intrinsically indeterministic. According to this interpretation, the act of observing or measuring an object is irreversible, and no truth can be attributed to an object except through the results of its measurement. This view has been challenged by the many worlds interpretation proposed by Hugh Everett III. According to Everett, the wave function of a quantum system describes a reality of many worlds, where objects exist in multiple states simultaneously and there is no wave function collapse. This deterministic view is at odds with the probabilistic nature of quantum mechanics, raising questions about the role of probability in the many worlds framework. As we continue our journey through the philosophical landscape of physics, we now turn our attention to the philosophy of thermal and statistical physics. This branch of philosophy delves into the foundational issues and conceptual implications of thermodynamics and statistical mechanics. These fields address the macroscopic behavior of systems comprising a vast number of microscopic entities, such as particles, and the nature of emergent laws like irreversibility and entropy. Philosophers first became interested in statistical mechanics due to an apparent conflict between the time-reversal symmetry of fundamental physical laws and the irreversibility observed in thermodynamic processes, a dilemma known as the arrow of time problem. How can the asymmetric behavior of macroscopic systems, like the tendency of heat to flow from hot to cold, be reconciled with the time-symmetric laws governing individual particles? Another central issue is the interpretation of probability in statistical mechanics. Are these probabilities epistemic, reflecting our lack of knowledge about the precise microstate of a system? Or are they ontic, representing an objective feature of the physical world? The epistemic interpretation, also known as the subjective or Bayesian view, posits that probabilities in statistical mechanics are a measure of our ignorance about the exact state of a system. According to this perspective, we resort to probabilistic descriptions due to the practical impossibility of knowing the precise properties of all its microconstituents, such as the positions and momenta of particles. Thus, the probabilities are not objective features of the world but arise from our ignorance. In contrast, the ontic interpretation, also called the objective or frequentist view, asserts that probabilities in statistical mechanics are real, physical properties of the system itself. Proponents of this view argue that the probabilistic nature of statistical mechanics is not merely a reflection of our ignorance, but an intrinsic feature of the physical world.